Mathematical models are powerful tools because they allow us to predict the future. Models map between inputs and outputs of systems and can be derived from first principles or learned from data. We use models to quantify some essential variable that is useful to us to accomplish a task, not to provide a faithful description of the exact reality of all the physical processes going on. The DuckyBot is a differential drive robot. The motion of each wheel is controlled by one DC motor. DC motors receive voltages as inputs and produce torques on the motor drive axis that spins the wheels. The movement of the wheels will produce an evolution of the robot's pose over time, which is what we want to quantify. Through these models, we can answer two questions. The first one is, given a sequence of commands to the wheels, how will the robot move? On the other side, if we want the robot to move in a certain way, which commands to the wheels should we send? We know that the pose of a robot is the position and the orientation of the body frame with respect to the world frame. We define the robot body frame so that the origin, A, is in the mid-axle point. We assume that the robot is symmetric along its longitudinal axis, and we take it as the x direction of the robot frame. Therefore, the wheels are assumed to be identical with diameter 2r, and both will be at a distance L from point A. The center of mass of the robot will lie on the x-axis and will be at a distance c from A. We assume that the robot's chassis is rigid as well. This means that the distance between any points of the robot does not change over time. To obtain the world's frame-based representation, we first determine the velocity of point A in the body frame. We can then move from the body frame to the world frame by using the rotation matrix defined by the orientation angle theta. To simplify this model, we make an additional pure rolling assumption. This is a strong assumption, and it implies that, first, the robot does not move sideways. So the lateral velocity of point A in the robot frame must be 0. And second, that the wheels do not slip. No slipping implies that for every full rotation, each wheel travels a distance that is equal to its circumference. So at every instant, the linear velocity of the wheels is given by their radius times the angular velocity of each wheel. The no sideways movement allows us to simplify the relations between robot and world frame. No slipping, instead, allows us to determine relations between the velocities of the wheels and those of the robot. We observe that while the robot is rotating without slipping, all of its points have velocity equal to the angular velocity of the robot, omega, times the distance to the instantaneous center of curvature, which is the only point that does not move in a rotation field, and a direction that is orthogonal to that identified by the center of curvature. By deriving the distance of the instantaneous center of curvature as a function of the wheel's linear velocities, we can gain some insights. When the linear speeds of the wheels are the same, the distance d is undefined. In fact, the robot is not rotating, but it's going straight. If the wheel velocities are equal but of opposite signs, then d is equal to 0. So the robot will rotate on the spot. If any of the wheel velocities are 0, then the center of curvature lies on the position of the static wheel, making the robot turn on the wheel. From the same expressions, recalling the implications of no wheel slipping, we can express the vehicle velocity as a function of the wheel angular velocities, which are what we ultimately command. We can now map the pose to wheel commands, or the forward kinematics of a differential drive robot, which is particularly useful when determining future estimates of the state. The inverse kinematics model, obtained by inverting the relation between wheel and vehicle velocities, allows us instead to map the desired vehicle velocities to-wheel commands, which is particularly useful in controlling the robot. The next step is determining the relationship between the actual commands we send to the wheels, which are voltages, and the angular velocities of the wheels. DC motors convert electrical energy and mechanical energy, and they are composed of a stator and a rotor. The stator hosts permanent magnets, and the rotor, which is placed inside the stator, is composed of coils. The rotor is connected to the motor shaft, which in turn is connected to the wheels. When voltage is applied to each coil, the current flow generates a torque, which is transmitted to the motor axis. The motor can be modeled as an RL circuit having two sources of voltage, the input provided by the user and the back EMF induced by the rotation of the shaft, which resists the motion. Motor equations include an electrical and a mechanical subsystem. The electrical one is obtained through the Kirchhoff laws, the mechanical one by imposing equilibrium of torques on the rotating shaft. These models include several constants, which are typically determined experimentally. The dynamics of the motor is much faster than that of the robot, so we can assume steady-state behavior. By neglecting the derivative terms, we obtain an instantaneous relationship between the applied voltages and the wheel angular velocities. We have derived a usable model for a differential drive robot, mapping the voltages to each motor to the evolution of the pose in the world frame. It is important to remember that a number of simplifying assumptions were made in order to obtain this model, defining its limitations. A key takeaway of modeling is that all models are wrong, but some are useful.